Welcome back to Simple GAN. In today's video, we'll dive into the intricate flow sheet of a merchant oxygen plant. This facility is truly the heart of industrial gas supply, playing a critical role across various sectors, including steel manufacturing, healthcare, and the chemical industries. Understanding its operation is key to appreciating modern industrial processes. We will meticulously break down each and every component, tracing the journey of air from its initial intake all the way through to the final liquid oxygen storage. This will be presented in an easy-to-understand, sequential flow. If you are an engineer, a student, or a plant professional, this detailed explanation is for you. So stay tuned and prepare to learn. A merchant oxygen plant fundamentally relies on cryogenic air separation technology. This advanced process is designed to efficiently separate the atmospheric air into its primary components, approximately 78% nitrogen, 21% oxygen, and about 1% argon. This separation is achieved by exploiting the distinct boiling points of these gases at extremely low temperatures. The overall process involves a series of critical steps. Air is first compressed to increase its density, then purified to remove contaminants, subsequently cooled to cryogenic temperatures, liquefied, and finally distilled. This multi-stage approach is essential to produce high-purity oxygen, which is vital for numerous industrial applications. The entire process begins with air intake, where atmospheric air is drawn into the system. It then progresses through compression, followed by thorough purification. Next, the air undergoes significant cooling, leading to liquefaction, and finally, distillation to separate the gases. The purified oxygen is then moved to storage and subsequently prepared for dispatch. Within this complex system, several key stages and components are crucial for its operation. These include the powerful air compressor, the efficient aftercooler, the specialized air purification unit, a series of heat exchangers, the critical expansion turbine, the sophisticated distillation column, the secure liquid oxygen tank, and the versatile vaporizer. Each plays a vital role in the overall process. The process commences with atmospheric air being drawn in through intake filters. These filters are essential for removing particulate matter like dust and any moisture present in the air, ensuring a clean input. Following filtration, the air is compressed to a pressure of 6 to 7 bar in a multi-stage compressor, significantly increasing its density and temperature. After compression, the now hot, compressed air flows into an aftercooler. The primary function of this unit is to efficiently remove the heat generated during the compression process. By cooling the air, the aftercooler prepares it for the subsequent purification stages, where lower temperatures are often beneficial for contaminant removal. Within the air purification unit, the compressed and cooled air passes through specialized molecular sieve beds. These beds, typically composed of materials like alumina and zeolite, are highly effective at adsorbing and removing critical impurities such as carbon dioxide, residual moisture, and various hydrocarbons, which could otherwise freeze and block equipment at cryogenic temperatures. The purification system operates with 2 molecular sieve beds in an alternating cycle. While one bed is actively purifying the incoming air, the other is simultaneously undergoing regeneration. This regeneration process involves using a stream of waste nitrogen to purge the adsorbed contaminants, ensuring a continuous supply of clean, dry air for the rest of the plant. Following purification, the clean air is directed into a series of heat exchangers. Here, it is progressively cooled to extremely low temperatures, typically ranging from -170 degrees Celsius to -190 degrees Celsius. This cooling is achieved through a highly efficient counterflow exchange with cold waste nitrogen streams, maximizing thermal energy recovery within the system. A crucial component in achieving cryogenic temperatures is the expansion turbine. This turbine provides the necessary refrigeration by allowing a portion of the air to expand rapidly. This expansion causes a significant drop in temperature, leading to the partial condensation of the air, which is a vital step before it enters the distillation column. The cooled, partially liquefied air then enters the cryogenic distillation column, specifically the high-pressure column. Inside this column, nitrogen, with its lower boiling point, begins to vaporize and rise towards the top, while oxygen, having a higher boiling point, condenses and collects as a liquid at the bottom of the column. The oxygen-enriched liquid from the high-pressure column is then transferred to the low-pressure column for further refinement. Here, a more precise separation occurs, ultimately yielding oxygen with an impressive purity of 99.7%. Additionally, argon, another valuable atmospheric gas, is carefully tapped from a specific section in the middle of the column. Once separated and purified, the liquid oxygen, maintained at an extremely cold temperature of -183 degrees Celsius, is safely stored in large, specially designed vacuum-insulated tanks. These tanks are engineered to minimize heat transfer from the surroundings, ensuring the liquid oxygen remains in its cryogenic state for extended periods. From storage, the liquid oxygen is dispatched in two primary forms. It can be loaded directly into specialized cryogenic tankers for transport as a liquid, or it can be vaporized into its gaseous form. This gaseous oxygen is then delivered via pipelines or compressed into cylinders, with rigorous purity checks conducted before any delivery to ensure product quality. The operation of a merchant oxygen plant is energy-intensive, typically consuming approximately 1 kilowatt-hour of electricity per cubic meter of oxygen produced. However, the plant incorporates advanced energy recovery systems, primarily through the use of turbines, which help to recapture and reuse energy, thereby improving overall efficiency and reducing operational costs. Safety is paramount in a merchant oxygen plant due to the nature of the materials handled. Strict protocols include ensuring all equipment is thoroughly degreased to prevent combustion, installing pressure relief valves to manage overpressure situations, and exclusively using oxygen-compatible materials throughout the system. These measures are critical to mitigate fire risks and ensure safe operation. And that concludes our detailed exploration of the flow sheet of a merchant oxygen plant. We hope this deep dive has provided you with valuable insights into this complex and essential industrial process. If you found this video informative, please like, share, and subscribe to SimpleGAN for more in-depth engineering insights and explanations. Stay curious and keep learning.